we can start. All right. So first of all, thank you all for being here tonight. This is the second talk of the STEM lecture series. There will be 2 more talks next semester, one in February and one in April. And these talks are kindly supported by our institution, Endicott College, but especially by the STEM division with Dr. Top, Assistant Dean of Art and Sciences, and Amanda Finnegan, Academic Coordinator. So tonight it's my greatest pleasure, it's actually a joy for me, to introduce our speaker, Dr. Bruce Boghosian. So Dr. Boghosian has been a professor at Tufts University since 2000, and the breadth and the depth of his work reflect very clearly in his career path and his impressive list of accomplishments. Just let me mention some of those. He's fellow of the American Physical Society, foreign member of the National Academy of Sciences of Armenia, Tufts University Distinguished Scholars, and Dr. Boghosian has been 3rd president of the American University in Armenia, in Yerevan, from 2004 to 2010. He managed to get accreditation for the first American-accredited bachelor program in the former Soviet Union. When I first met Bruce, was in 2001 when I started my graduate program at Tufts, and eventually Bruce became my advisor, my PhD advisor, supervising my thesis in cellular automata. It's kind of hard for me to explain and convey with words what an inspiration Bruce has been for me, both professionally and from a personal point of view. So I'm very happy that he's here tonight. I think that he is a very unique combination of a brilliant mathematician, memorable teacher and mentor, and is a very kind spirit too. So these 3 things coexist in in one individual, which is amazing. So Bruce has done research in various fields, and his focus has been for a while in various aspects of fluid dynamics. But over the last few years, Bruce has undertaken the study of economics, and the results he will present tonight are, in my opinion, groundbreaking. So this is something completely new, and I think they're going to have, very deep impact in economics. So I'm not going to, spoil the plot for you of the story tonight. So I'm going to just leave the stage to Bruce. And so the title of the talk is The Transactional Origins of Poverty and Inequality. So, please.
Thank you very much, Gianluca, and likewise, it was a pleasure having you as a PhD student, and our friendship over the years has been wonderful. Thank you very much to Endicott College for your hospitality, the invitation to come here today. It's already been a pleasure. I'll try this evening to convey some of the point that Gianluca just made, how it is that somebody who is doing fluid dynamics ends up thinking about economics. The distance between them is not as great as you might think, and you'll see that in some of the upcoming slides. Let me first thank my research group. This was as of last year. I've had 5 graduate students and 1 undergraduate student working on this with me, and we have 2 more students, first-year students, in the group this year as well. I'll begin by discussing some statistics. Let me see if I get the laser pointer working. Yeah. About wealth inequality in the world and in the US today. And I'll discuss what I mean by mesoeconomics, sort of between microeconomics and macroeconomics. We'll talk a little bit about wealth distributions and how one measures wealth distributions, what one means by inequality, wealth inequality, how do you quantify that? And then the heart of the talk will be about models to try to explain the shape of wealth distributions, to try to explain the dynamics of wealth distributions, and the growth or the stabilization of inequality and how that comes about. And then a few words afterwards, discussion about these results afterwards, because although these results are mathematical and they're certainly related to economics, it's all grounded in empirical economics, at the same time, the ideas presented have impact in places that you wouldn't imagine. In the title of the talk, I have underneath mathematics, economics, physics, philosophy, and ethics. And in some sense, all of these things come in. The general idea is to apply methods from statistical physics to economics and to populations of people. And I'll explain a little bit of that. It has impact, I think, in economics, but it also raises questions about philosophy and ethics, the way we think about wealth, and the way we think about poverty and inequality generally. So I'll try to touch on those at the end of the talk. This first picture is an aerial photograph of a neighborhood in Mexico City. When people first see this, sometimes they think it's been photoshopped and there's really two pictures going on there. There isn't. There's one picture, and that's a fence running down through the middle of a neighborhood. And you can see that the housing on both sides of that fence is very, very different. Even though the neighborhoods are contiguous geographically, you might say that in wealth space, they're in very, very different places. You can see that from the cars parked in front. You can see that from the condition of the housing. You can see it from the trimmed lawns and so forth. You don't have to go to Mexico to see this. There are places in the United States where this picture could be taken. There are places in Europe, Eurasia, and Asia where this picture could be taken. This phenomenon is growing around the world, and we'll discuss a bit of that later. Let's start with some statistics. The top 1% of the world's population has about the same wealth as the bottom 99%. A more stark statistic is often quoted by Oxfam International. They time the announcement of this every January to coincide with the meeting in Davos, Switzerland. And they quote the number of people who possess wealth equal to that of the lower half of the world's population. So in 2010, they published that there were 388 people who had as much wealth as the lower half of the world's population. That's 388 people has as much wealth as 3.6 billion people. I'm sorry? No, combined. The 388 combined have that much, yeah. In 2014, that number was down to 85 people. In 2016, it was down to 62 people. In January of this year, it was 8 people, and the last I looked, it's more like 5 people. And at this point, you can kind of guess who they are. And there's few enough of them, and if you combine the wealth of 5 people, you get the wealth of 3.6 billion people. 7 out of 10 people in the world live in a country that has seen a rise in inequality in the last 30 years. So, there's many statistics like this in the newspaper on a daily basis. But what I've tried to do here, and what I do on the next slide as well, is to pick those that show that wealth distribution is dynamic. It's changing in time. It's not just that wealth inequality is large. It's large and it's changing. So let's look at the next slide. As of 2013, some of these figures are older. 75.4% of all wealth in the US was owned by the richest 10%. That number has changed a bit, but the last time we had good statistics was 2013. The 2016 statistics, these are published every 3 years, just came out a few weeks ago and we're still looking at them. In 2007, 1 of every 8 US children was on food assistance, and by 2014, that number was 1 out of every 5. Again, this points to a change in the inequality situation. In 1996, there were about 750,000 ultra-poor households in the US, ultra-poor being defined as living on less than $2 a day. Some of you may have seen the book by Barbara Ehrenreich on living on less than $2 a day. By 2015, that number had doubled to 1.5 million. In 2000, 7.2 million Americans lived in areas of concentrated poverty. That's defined as a neighborhood in which 40% or more of the households live below the federally mandated poverty line. By 2013, that number had almost doubled to 13.8 million. And finally, the most vulnerable segment of society, the number of homeless children in the US increased by about 60% between 2008 and 2014. Many of these statistics are results of the economic turbulence, the aftermath of the economic turbulence that happened in 2008. Here's another way to look at things, and this is a very clever statistic by Michael Norton at the Harvard Business School and Dan Ariely at Duke University. Look at the middle bar first. That is the wealth distribution that Americans think we have from a survey of a large number of people. The yellow bar is the top 20%, the orange bar is the second 20%, red is the third, light blue is the fourth, and purple is the bottom 20%. Americans understand that there is wealth inequality, and this is roughly what they think that inequality is. Now, how much inequality do they think there should be? When that question is put to them, and it's put to them in a very particular way that I'll describe in a second, this is what they would like to see. They would still like some inequality, and that should be noted. They do believe that there should be some spread in wealth, some spectrum of wealth, but they don't believe that it should be as great as it is. What they don't understand is that's the actual distribution of wealth in the United States. The top bar is what it really is, and you can see that something in the vicinity of 85% of the wealth is owned by the top 20% of the people. If you look at the bottom 40%, they almost don't show up. It's a few pixels wide at the bottom, the light blue and the dark blue curves. The bottom 40% almost don't register on the wealth spectrum in the US today. How did they ask this question, what they would like it to be? Here's an example where philosophy and ethics can come into a question like this. They use a method due to the philosopher John Rawls called the veil of ignorance. They ask you to set these bars to create the society that they would want under the condition that in this hypothetical society, you have to forget about what wealth you have or where you sit in society today. You create these bars, you create this society, and the rule is you could be dropped in it anywhere, right? So you could be dropped in it anywhere with, according to the distribution you create. You randomly sample from that distribution, and that's where you could end up. So under those rules, under those circumstances, what would you like the wealth distribution to be? That's what you get. Let's turn from these statistics to discuss a few terms here. I want to just quickly state, and I apologize to the economists in the audience because this is sort of the bread and butter for them, but definitions. Microeconomics is the economics of individual agents' behavior in decision making and resource allocation. You look at individuals, you look at transactions between them, You look at how they make their decisions, what their utility is for various outcomes of a transaction, and what the transaction ends up being as a result of that, including perhaps behavioral effects. Macroeconomics is more big picture economics. It looks at entire populations and societies. The emphasis is on big collective effects, such as supply, demand, prices, interest rates, exchange rates, etc. Now, societies are made of individual economic agents. So from a reductionist point of view, you might think that macroeconomics should be derivable from microeconomics, that there should be ways that if you know what the rules are at the individual level, you should be able to work from that to figure out how macroeconomies behave. We're not yet close to being able to do this. There are many situations where economists, macroeconomists in particular, will try to develop what they refer to as micro foundations for their theories. But we're far from the point where all macroeconomic phenomenon have known micro foundations. So are there historical examples that we can draw upon from other disciplines? Well, this is where the fluid dynamics comes in. I would like to make an argument that physics had exactly the same problem in the 19th and early 20th centuries. The connection between what is a fluid, like for example, the air in this room is a gas. At its lowest level, it's made out of molecules. But those molecules collide with each other and interact with each other. And as a result, we get something that behaves like the air in this room. It can flow, it can create vortices, whirlpools. If you go out of this room, you can get hurricanes and tornadoes. It can be turbulent, it can do all kinds of things like that. Is it possible to derive this from the microscopic level? Well, those of you who study chemistry might recognize the names of Dalton and Avogadro, who first thought of molecular theory, the idea that things were made of individual molecules carrying energy, back in the early 19th century. And the idea that molecules can collide with each other and exchange energy in those collisions dates back to the 1820s. But then this proceeded not just in two steps, not just micro to macro. There was an intermediate level. There was a mesoscale understanding of statistical mechanics that came about in the 1860s and 1870s when people like Maxwell and Boltzmann and Gibbs realized that energy distributes itself among the population of molecules in a very particular way. And a very good first thing to do to understand the behavior of air is to understand how the energy distributes itself among the molecules. Finally, once that was known, another 50 years elapsed until people like Chapman and Enskog were able to use that mathematics, the shape of that distribution, to actually derive the fluid dynamic equations. So in a little bit over 100 years, physicists went from just guessing that there were molecules at the bottom of everything to actually being able to derive the already known equations of fluid dynamics by about 1920. So microfluidics is the fluidics of molecules. Mesofluidics is what the energy distribution looks like. This is a probability distribution with energy on the x-axis. And that is a fairly realistic picture of what the energy distribution looks like. It's called a Maxwell-Boltzmann distribution. Macrofluidics is fluid turbulence and really the macro motion of fluids. They jumped, again, the theoretical underpinnings of jumping from that to that took about 100 years. Microeconomics is individual transactions between economic agents. The people are like the molecules in this metaphor. From the way that people interact and transact and exchange wealth with one another, rather than energy, you have wealth going back and forth, you get a certain distribution of wealth in society. And I'll describe what that distribution is shortly. And then from that, you get macroeconomic behavior. You get the behavior of markets. You get turbulence in markets. So the metaphor goes right across the board. And what I'd like to do in the next few minutes is to pursue that metaphor a little bit further. Any questions at this point? Okay, first of all, let's discuss how do you quantify a wealth distribution? So suppose that the bottom F% of agents in society hold L% of the total wealth. And the idea of plotting L versus F is due to the American economist Max Lorenz, who thought this up while he was doing his PhD dissertation at the University of Wisconsin-Madison back in the early 1900s. And the idea is you plot the fraction of people versus the fraction of wealth versus the fraction of people holding that wealth, where the people are rank ordered from the bottom up. So to give you two examples that make this clear, let's suppose you had a hypothetical society where everybody had exactly the same amount of wealth. Then 0% of the people would have 0% of the wealth. That's always true. So these curves always go through 0. But if everybody had exactly the same percent of wealth, exactly the same amount of wealth, then a quarter of the people would have a quarter of the wealth, half of the people would have half of the wealth, 3/4 of the people would have 3/4 of the wealth, and all of the people would have all of the wealth, and you would get a straight line. So this straight line is a hypothetical, economically egalitarian society where everybody has precisely the same amount of wealth. Let's go to the other extreme. Suppose you had a total oligarchy. One person has all the wealth, everybody else has 0. In that case, this Lorenz curve would be the green curve that you can hardly see here and shouldn't even be called a curve. It actually is flat, dead-lined all the way across from 0 to 1. And at the last minute, it jumps up to 1 because the oligarch has all the wealth. So essentially, a negligible fraction of the people have all of the wealth. Everybody else has 0 wealth. What do real Lorenz curves look like? Well, as you might imagine, they're somewhere in the middle between those extremes. There are no total oligarchies in the world, and there are no totally egalitarian societies in the world. Those are just put there to be the two extremes that bracket this thing. From this, one can derive something called the Gini coefficient, named after Corrado Gini, who also did most of his work in the early 20th century. And starting from the Lorenz curve, what he said is, let's use the area in this plot, the area between the real Lorenz curve and the hypothetical ideal egalitarian Lorenz curve, let's use that area as a measure of inequality. And that measure is, twice that area is called the Gini coefficient. And you may read about the Gini coefficient in newspapers when people talk about wealth inequality, the Gini coefficient of this country versus that country, or the Gini coefficient of the US is this. And what they really mean is twice the area of that curve. Why twice? Well, because the worst it can be is a total oligarchy, in which case the entire lower triangle is shaded. This is a 1 by 1 square, so it has area 1. If the lower triangle is shaded, that has area 1/2. If you double that, you get 1. So a Gini coefficient of 0 is complete equality, and a Gini coefficient of 1 is a total oligarchy. And the question is, where do real wealth distributions fall in the middle of this? Well, there is a real wealth distribution. That's the wealth distribution. That red curve is the wealth distribution of the United States in 2013, and it corresponds to a Gini coefficient of about 85, 86%. Now, one catch, if you read about Gini coefficients in the newspapers, one thing that you should note is that they're often quoted for income. Here I'm talking about wealth. income Gini coefficients are always lower than wealth Gini coefficients. I think the income Gini coefficient of the US is in the upper 40% range, but the wealth Gini coefficient is closer to 86% as of 2013. There's one other feature on this that you can barely see, but I want to point it out to you, and that is that if you look closely, the curve actually goes slightly downward at the beginning. It has sort of a negative slope at the beginning, and then it begins to go up. And the reason for that is we actually have negative wealth agents in the US. About 11.5% of the US population is underwater. Wealth, that doesn't mean that they're living in poverty necessarily. It just means their liabilities are greater than their assets. Maybe they have a mortgage on a home and the home has dropped in value, and they owe more on the mortgage than the home is worth. That could put them in a negative wealth situation. About 11.5% of the population is in that situation. That negative wealth, the dip in that curve at the beginning, is going to play a role shortly. So now I need to, let me just put my phone here so that I can see what time it is and time the talk accordingly. I want to give you, I want to go now from how wealth distributions are measured to actually giving you a dynamic model, the model that we're using, and I'll build it up in 3 stages for what wealth distributions look like. So first of all, we have to talk about how wealth changes hands, how the distribution is built up. If I give you a car worth $5,000 and you give me $5,000, then arguably no wealth has changed hands. But one of us may overvalue the car, undervalue the car, and if that happens after the transaction, a small amount of wealth may move from one of us to the other. We might overpay. You might accept something less than what the car is really worth. There's other reasons this could happen too. The deal could go forward based on what the car is really worth, and then you could drive it a block away from the transaction, and the engine could blow up. And nobody knew in advance that was going to happen. Of course, if somebody knows in advance that's going to happen, well, that's sort of less ethical, but that's because the seller has there's asymmetric information going on. The seller has more information about the condition of the car than the buyer. All of these are reasons that wealth could go back and forth from one person to another. So let's assume that the movement of wealth is due to such mistakes. And in fact, let's throw away the car. We're going to say that the amount of wealth that moves from one to the other is delta W. If the car is worth $5,000 and I get it from you for only $4,900, the delta W is $100 that goes from one person to the other. Let's throw away the car and just focus on the delta W. Okay, so think of now transactions in a society as little delta W's moving back between people due to mistakes, due to asymmetric information, due to all the things that we discussed. So what a class of models does, the class that we're looking at, they're called asset exchange models. You start with a population of n agents, and let's give that population of n agents a total wealth, capital W. And here's how you do it. You select 2 agents randomly, and you're going to have a transaction between them. And a delta W will move back and forth from one to the other. Then you select another 2 randomly, and you do the same thing. And then another 2, and another 2, and another 2. You pick 2 agents randomly, they have a transaction, the delta W moves, and you just keep repeating. Now, to describe this, I have to tell you 2 things. I have to tell you that after I pick 2 agents, how do I determine what the delta W is that's going to move between them? And I have to tell you, how do I determine which agent wins and which agent loses? So let's see how to do that. The basic model that we're going to use in this work is due to Anirban Chakraborty, who published this in a short paper back in 2002, and we're using this idea as the launching point for our model. Here's the reasoning. Agents can't lose more wealth than they have, so the amount of wealth that changes hands, this delta W, has to be a fraction of the wealth of the poorer of the two agents. Here's another way to say that. If I'm engaged in a transaction with Bill Gates, the fraction of money that could go back and forth between him and me is going to be a fraction of my wealth and not of his, right? I can't afford to engage in some of the transactions that he can afford to engage in, obviously. Typically, most rational people don't sort of bet the farm, as they say, on one single transaction. Most people don't stake a large macroscopic fraction of their wealth on a single transaction. I know that some people do these things. Some people engage in leveraged transactions and so forth. But I think we can kind of neglect such people because there's few of them.
This accounts for the negative sloping of your
Well, yes, exactly. And we have to come back to that because if we make it, and it's astute of you to notice that if we make this assumption, nobody can go negative. And so that's the first thing we're going to do. We're going to assume that the delta W is proportional to the wealth of the poorer of the two agents. Second thing the second bit of information I have to give you about the model is how do you decide which way it goes? And for the first version of this model, the version that Professor Chakraborty came up with, we decide who wins by flipping a fair coin. Nobody wants to lose money. Nobody is going to enter a transaction with the goal of losing wealth. Rational people don't do that. Everybody's trying their best, but some people can make mistakes. Now, let's assume that everybody is about equally as skilled at making transactions as everybody else. Because if we didn't assume that, if we assume that some people are better at it than others, or some people are smarter than others, wealth will surely concentrate to those people. What I would like to do here is give the market that we're trying to create here every benefit of the doubt and say everybody's equally smart. We're going to flip a fair coin to decide on the direction that delta W goes. Delta W is chosen as a proportion of the wealth of the smaller agent, but it could go either way with equal odds. So the first question, let's see if I can do this. Is what do you think will happen if I do that? I'm going to take a chance here and show a live simulation. This is not a video. This is not pre-recorded. This is the computer running in real time. It's always dangerous to do that. Let's see if it works. I'm starting off with 32 agents. All of them have wealth 1. I'm going to pick 2 of them randomly, and I'm going to take, so 32 agents, I'm going to take 2.5% of the wealth of the poorer of the 2 and flip a random coin and move it to one or the other. What do you think is going to happen? When I ask this question to classes at Tufts, if they don't catch on, if they don't sort of game the answer, typically half of the students think nothing will happen. It'll fluctuate, but it'll reach a stable distribution. It'll stabilize.
That's what happens sometimes. It's kind of random.
It's random. It'll surely fluctuate a little bit, but the other half of the class are the cynics who believe that somehow all of it will end up in the hands of one person. Now, I don't know if they're really cynics or if they're taking their cue from the fact that the vertical scale of this graph is about 32. But There it goes, and you can see the number of transactions at the top here. We're up to about 200,000 transactions, 500,000, 750,000. We're approaching 1 million transactions now, and there's still 3 duking it out. You might notice that the majority of the 32 have been ground into the dust at this point. And now we have sort of Bill Gates and Warren Buffett here that are at this point, either of those two could win, but one of them will win. We're up to 3 million transaction steps. It's closer to 10 million or so before you can't even see 31 of these, and the 32nd has all the money. Now, how do we know which one the 32nd is? Well, it could be any of them with equal odds. If I started off this simulation again, well, I think we're there now. In 5 million already, you can see one has emerged as the oligarch. If I start this simulation again, which I'll do now, it'll be another one that ultimately, most probably, that's right. So, now this one looks like you could bet on that one.
You could set up a gambling ring just watching.
You could do that. But one thing is for sure, I mean, which one wins, you have a 1 in 32 chance. But this is clearly a toy model. Let's stop this if I can and go back. The process seems fair. So why does wealth concentrate in this model? That's where the mathematics comes in. Here's the best that I can do to explain it, and I apologize for the fact that it's not very good. There is, the mathematics is unequivocal. I mean, you can see it mathematically why this is the case. But here's one way to think about it. There's a false argument that I'd like to give you for this. The false argument is, well, suppose I have an agent with $1,000 and an agent with $100. And suppose the fraction that we're going to take of the lower one is 10%. Well, the lower one, the $100 agent, could lose 10% of his or her wealth, whereas the richer agent, the one with $1,000, will end up losing only 1% of his or her wealth because the amount of money at stake is $10. It's 10% of the $100. If the $100 person loses it, they're losing 10% of the wealth, whereas if the $1,000 person loses it, they're losing only 1% of their wealth. Now, here's why that's a false argument. It's a false argument because I could turn it around and I could say if the poorer agent wins, they're winning 10% of their wealth. Whereas if the richer agent wins, they're winning only 1% of their wealth. Then it doesn't sound so good for the richer agent. The reason this happens is that those two effects don't exactly cancel out. If you include those two effects, there's a higher order term that comes in that favors the richer agent over the poorer agent. And to get into that, it's more mathematics than I'd go to here, but if you're interested, just come to me afterwards and I can show you. Here's another way to view the concentration of wealth. This is the logarithm of wealth. I'm sorry that it's kind of difficult to see that axis. This is 1 is here. This is where they all start out. And I've got 10 agents. 10 is here. It's a logarithmic scale, so everything is going down by a factor of 10. That's 10, 1, 1/10, 1 100th, 1 1,000th, 1 10,000th, etc. The richest agent is the one at the top here who ends up at about 10 with all the wealth. Here's what all the other rank agents are doing. They're all sort of decreasing. And notice that the wealth of the poorer agent is going down the fastest. However, it is possible for them to cross each other. These are colored according to the rank, so the identities of the agents are not the same as the colors. If two curves cross, the color and the person won't necessarily stay the same. You're coloring here according to rank and not according to which agent it is. So it's very possible that right there, for example, these two agents crossed. That can happen. But we're interested in averaged statistics. So let me run this 10,000 times and show you the same thing all averaged up. And now it's very clear what's going on. The poorest agent's wealth is going down reasonably rapidly. Again, this is a log scale versus time. When you have a straight line on a log scale, that's an exponential decrease. The richer you are, the longer the time constant on the exponential. The poorest agent is losing wealth most rapidly with the shortest time constant. The richer agents are losing it with slower time constants, and the wealthiest agent isn't losing it at all. The wealthiest agent is just vacuuming it all up and ends up at a wealth of 10. We were actually able to prove a theorem in 2015 that for this model, from any initial condition whatsoever, the Gini coefficient is provably non-decreasing and will approach 1 in the long time limit. You've already seen that in numerical simulations. This shows that one person will run away with all the wealth. I'm sorry? Yeah, no matter what you started with. If you started off with a non-uniform distribution, if in your initial conditions some had more than others, the ones that had more in that initial condition would have a real advantage. It would no longer be a 1 in 32 probability. The ones who had more to begin with would have an inherent initial advantage. So in this model, there is an inherent endogenous downward pressure on economic agents. The poorer you are, the greater that downward pressure. It's built into the model. However, as I said earlier, a complete oligarchy is unrealistic. There are no countries that have a complete oligarchy where one person has all the wealth. That's totally unrealistic. Let's try to fix it by introducing some redistribution in the model. So to introduce redistribution, what I want to do is to tax the wealth of both agents at a fixed rate, chi. So I'm going to charge a wealth tax on both agents in the transaction and put it in a pool. And every so often I'm going to take that pool and I'm going to chop it up into capital N pieces and redistribute it equally amongst everybody. This is a simple model of redistribution. It's like a wealth tax that gets redistributed. So it follows that agents above the mean are paying net tax. They're paying more in tax than is redistributed to them. And agents under the mean are receiving net benefits. What happens? Well, this redistribution will stabilize the model that I just showed you. We're going to keep the same model and just put in this wealth tax, and now you will get stable Lorenz curves. And as you might guess, the larger the tax, the more the Lorenz curve moves upward toward the diagonal. Here's another way to say it. The larger the tax, the lower the Gini coefficient. Now, notice that if your tax is very small and your Gini coefficient is very high, you can lower the Gini coefficient appreciably by adding a little tax. But if you add too much tax and you're out on this tail, then you get diminishing returns. Increasing the redistribution won't lower your Gini so well anymore. So taxation is a way to lower, and redistribution is a way to lower the Gini, but only if you're in a high Gini situation. Well, the US, we said, is about 86%. More redistribution would significantly lower the US Gini coefficient if there were a will to do that. Yep. Here, yeah, I'm sorry, that should be chi. That's the amount of the tax. Ta and chi are the same thing. At some point, we changed the nomenclature in our papers, and this graph didn't get the memo yet. So now we can ask a question. I mean, that lower curve there doesn't look too bad. Can we play with chi to fit the US wealth distribution in 2013? I would add, for example, before I go on, I would add that other parameter, beta, the percentage, the thing that was 2.5% in the simulation, doesn't matter so much. If you lower that beta and wait a longer time, you get the same answer. All beta does is change the time scale. If I lowered that percentage from 2.5% down to 1.25%, I could run it longer and get basically the same curve. So the final distribution doesn't depend on the beta, but it does depend on the taxation chi. So by tinkering around with chi, can I make that work? So the red curve here is the empirical US wealth data in 2013, and the blue curve here is what you get with the model for a chi of, didn't I put it here? I'm afraid I didn't, but I think the chi was about 2.5%. Now, I would argue that's not too bad. The biggest mistake that's being made here is about a 2% mistake across the board. The inset here shows the error that you get across the board as a function of the same x-axis that you have here. So this Lorenz curve isn't too bad, but it's not that great either. You can see that the Lorenz curve that we're getting from theory, this blue dashed curve, is higher at the upper end of the wealth spectrum, lower in the middle of the wealth spectrum, and higher again at the bottom of the wealth spectrum. Okay, so it's not, I mean, it's better than you might think it would be for such a ridiculously simple model. Suddenly the model is not looking like a toy model anymore. Let's see if we can make it better. The next, and by the way, there's one other thing I'd say. You might wonder why these curves are so smooth. I was doing Monte Carlo simulations, and those always seem to be noisy. Why are these curves so smooth? The answer is that with this mathematical model, we have a better way to get the answers than doing a Monte Carlo simulation. We can define a partial differential equation that is obeyed by these curves and then numerically solve it on the computer to get perfectly straight curves as though you did the Monte Carlo with a ridiculously large number of agents. So that's why the curves are smooth. Here's the next modification that I want to put on the model, and it's called wealth attained advantage. Let's suppose the coin flip is not fair but favors the wealthier agent. Instead of a 50-50 coin flip, I want to bias that coin toward the wealthier agent by a certain amount. How do I do that? Well, first of all, why do I do that? Wealthier agents attain a higher percentage return on investments. They get lower mortgage rates when they take out mortgages. They receive better financial advice than poorer agents. They avoid taxation through loopholes more effectively. And in the most egregious scenario, they're able to go to K Street and hire a lobbyist and influence legislation so that they don't have to pay as much in taxes or they get more beneficial treatment. Conversely, poorer agents have less time to shop for the best prices. If you're holding down 2 jobs, you don't have time to search for the lowest priced gasoline in town. They end up paying higher interest rates. Sometimes they pay higher rents. Sometimes they lose their security deposits. As the author Barbara Ehrenreich said, it's expensive to be poor. And so this creates a natural bias in the coin. Can we get any better by introducing a bias? It's not difficult to put this in the mathematical model. The probability of the wealthier agent winning, we make greater than 1/2, and the poorer agent winning less than 1/2. Now, how do we bias that? Well, we make the bias proportional to the wealth difference between the two agents, and we call the proportionality constant zeta. Getting sort of a lesson in the Greek alphabet here. Zeta is the proportionality constant that measures the wealth attained advantage. If zeta is 0, there's no wealth attained advantage, you're back to a fair coin. Positive zeta means that the wealthier agent has an advantage. WAA is our abbreviation for wealth attained advantage. Now, an interesting thing happens here. If zeta is less than chi, if wealth attained advantage is less than redistribution, you get a normal Lorenz curve that starts from 0 and goes to 1. Now, here the redistribution is 0.2. So the first 5 curves here, where zeta is 0, 0.05, up to 0.2, start at 0, 0, and they end at 1, 1. But then a very interesting thing happens to the solution to this when zeta is greater than chi. The Lorenz curve hits the right-hand side below 1. What does that mean? It means that there's an oligarch there. But now it's a partial oligarch. This blue curve in the middle, for example, hits the right-hand side there. That's at about 70%, which means in that society, 30% of the wealth is in the hands of a negligibly small number of agents, and the rest of the people are distributed normally. That happens when wealth attained advantage is greater than redistribution. I had students who referred to the wealth attained advantage coefficient as the corruption coefficient. So what this is telling you is that if corruption is greater than redistribution, you'll have oligarchs. And if corruption is less than redistribution, you won't have oligarchs. Oligarchy is qualitatively different from a normal wealth distribution. It's not just people being very rich. It's a singularity in the wealth distribution that appears as a sharp phase transition when one of these parameters exceeds the other. So now we have 2 parameters. We have redistribution and wealth attained advantage. Fit it to the US data, and what do you get? That's the best fit for the 2013 data, and you can see 2 things happened. First of all, the curve is very, very good near the top. We're getting very, very good agreement for the wealthiest part of society. Most of the mistake is moved down to the bottom. The other thing that happens is that we are getting an oligarchy. According to this model, if you believe this model, the US is an oligarchy where about 30% of the wealth is held by a vanishingly small number of agents. The red one is the real one, and the blue one, yeah, so now you can see why we're having a problem down here is we don't have negative wealth in this model. And as I said, 11.5% of the US population is negative wealth, and now that has become a real problem for us because we're not getting the bottom right. So how do we fix that? We have something we call the affine wealth model, and it works like this. We're going, instead of making the lower bound on wealth 0, we're going to make it negative S. And here's what we do. At the beginning of each transaction, both agents will add S to their wealth. Now their wealth will be positive. Now the transaction proceeds as before, and after the transaction, you subtract S from both of their wealth. Now the constant S is taken to be C times the average wealth, and C is now our new parameter. And now we fit to that. And that's what we've got. Again, the red curve is the Fed data from 2013. The blue dashed curve is a fit for these 3 parameters. And it doesn't look bad to me. The agreement is within, as you can see here, about 0.5%. And that's to real wealth data. So let me just finish by discussing this a bit. This inequality is due to symmetry breaking. As you saw, you could start with a symmetric group of agents, and the symmetry would break, and one of them would end up being the winner. The model naturally explains the phenomenon of oligarchy, and it explains why upward mobility decreases as inequality increases. The model works for different countries and different epochs. We've tried US data going back to 1989. The agreement is similar. We've gotten data from the European Central Bank, and it works for many countries in Europe. There's much more to the data, to the model, but let me not go into that. One question that I've gotten is this realistic? The way one person put it to me, do you really mean to suggest that if you give each of N people $100 and lock them in a room, when you open the door later on, one person is going to have all the money? My answer to that is yes, I do. Because the experiment actually has been done and the results are in. And it's been done, intentionally or not, on the 287 million inhabitants of the Soviet Union in 1991. They were metaphorically locked in a room. They started out with a reasonable level of economic equality, far from perfect, but it was a socialist economy. And in a very short period of time, government ownership and regulation were removed very quickly. What happened? You might think that under those circumstances, the US would introduce something like the Marshall Plan, which rescued many European countries who were economically devastated after World War II. The Marshall Plan involved an investment of 18 billion US dollars. In inflation-adjusted dollars, that'd be 120 billion today, which seems to me, in retrospect, like a real bargain for picking up some of the US's most reliable Western European allies. So you might think with that successful example behind them, that with that example to draw on, they would do a similar thing for the 15 former republics of the Soviet Union and try to get 15 new thriving market economies. But instead, what was done was called shock therapy economics. No Marshall Plan would be needed. See, the US had become a very ideologically different place between World War II and 1991. It was really believed, mostly by neoconservative economists in 1991, that markets were utterly stable. And if you just leave them to their natural process, it would create a stable, thriving market economy. And so these states of the former Soviet Union were told to abandon state planning and free up prices, promote private competition, and sell off state industry as fast as possible. And these were not just suggestions. The IMF and the World Bank made these preconditions to development loans, so these countries raced to do these things as fast as they could. What happened? A drastic decrease in industrial output, a near halving of the USSR's GDP and of personal incomes, skyrocketing unemployment rate, doubling of the suicide rate, a 12.8% death rate increase among males in just the 2 years following 1991, and massive emigration that lasts to this day. Empty factories, factories that were bought quickly by foreign investors, gutted of their copper and anything metal that could be removed from the walls, and employees fired. Those factories are shells that remain there to this day. Those pictures were taken this summer. The best theories of economics say that markets are stable in a supply-demand equilibrium. But I just showed you a model that explains empirical data well by assuming they are completely unstable and they reach a steady state only due to redistribution. Another discussion point. Are wealth distributions due only to differences in choices, differences in utilities, differences in decisions people make? Well, according to neoclassical economics, a hypothetical population with identical utilities and equal initial endowments would be in a statistical steady state. The trade between such people would be very low because it's already in a Pareto equilibrium. Making one person happier would make another sadder. But in asset exchange models, you could have a population of people with identical utilities, equal initial endowments, and the symmetry would break. Some would become wealthier, some poorer. Saying that identical people must have identical wealth is as absurd as saying that identical atoms in a gas must all have the same energy. I have a gas of argon atoms in a jar. They're all identical. They're argon atoms. How can they be different? If they're identical, they must have equal energy. No. Some of them will be slow, some of them will be fast. And the same thing happens with wealth. Finally, a philosophical doctrine called voluntariness comes off of this. According to voluntariness, our wealth is the result of a sequence of transactions that we've made during our lives. And we enter into these transactions voluntarily. Nobody forces us. Hence, we have nobody to blame but ourselves for the outcome. And yet, we've shown that a symmetry-breaking model of wealth transfer explains accurately the current shape of the wealth distribution. And after the symmetry initially breaks, there's a subsequent strong downward pressure on poorer agents. And I would argue this casts great doubt on this notion of voluntariness. Let me go on to the conclusions. Asset exchange models are simple mathematical models of wealth distribution, and despite their simplicity, they seem to be remarkably accurate. They challenge the economic orthodoxy of supply-demand equilibria in favor of a totally unstable distribution that is stabilized only by redistribution. They really suggest that we need to rethink our attitudes about wealth in fundamental ways. And I think mathematical models like this one can teach us a great deal about not only mathematics, but economics and ethics of poverty and inequality. Thank you very much for your attention. I'm sorry I went over time.
Yeah, we have time for a few questions. Chris?
Can you go back a couple slides? One more? Let's see. No, okay.
Is that the one?
Yeah, maybe up one. Sorry.
Up, forward, or backward?
Oh, sorry, forward toward the end. Yeah, okay.
Voluntariness, yeah.
Okay, so maybe I can't find the slide, but I'm wondering, you said several times that, if you believe that model, but your model matched the data.
Well, that's why I think it's believable, yes. Yeah.
That's real strong evidence for the correctness of your model. How could you strengthen this evidence? I guess make it fit.
Well, it's a three-parameter model. I suppose if you could come up with a two-parameter model, then by Occam's razor, that would be better, but we haven't been able to do that. Still, I think a three-parameter model that allows you to match a whole curve is not too bad.
Yeah. It seems like super believable. Like I believed it, and then you said you believe it. Okay, yeah. So
Well, I have to say that from politeness because it's my model, so others have to make that judgment. Yes?
How do those parameters match up with versus we know about the United States? So, for example, to incorporate debt, that kind of models something more banks. How does your C parameter match up against what we actually experience?
Well, because of the fit, the 11.5% figure matches very well between the two curves. They both reach their minimum at the same point, that very shallow minimum at the same point, which is the 11.5% point. As far as what the wealth distribution looks like for negative wealth agents, in bulk, it's not too bad. If you look at, for example, extreme values, I think the most underwater person in the United States is underwater by more than $200 million. That person is not well captured in this. I have a sense that that person probably lives a very good life in spite of the fact that they owe $200 million. People that work with that amount of money, whether they happen to be above or below zero, tend to do well. I think at that level, broke is a temporary inconvenience. So at those extremes, those are not quite captured, but that's an extreme. The distribution as a whole matches reasonably well. At the very top of the distribution, again, if you go to the extremes in either direction, the trouble is that you have bad statistics there because there's so few people at those extremes. And so it's hard to tell. I would add, by the way, that the problem of a paucity of data plagues this field. There are only 20 countries in the world that ask for wealth information on their household surveys that are conducted by their central banks or their ministries of statistics. Most of the countries in the world, the other 160 plus countries in the world, don't even ask for the information on household surveys. So we've been sticking for the moment to those 20 countries. Now, economists have ways of inferring wealth data from income data, which is collected well, consumption data, and so forth. And we're looking into using those, but we don't trust those as much as the 20 countries that get wealth data from the household surveys. The reason that income data is so much better than wealth data is most countries have an income tax, so people declare their income data. Very few countries in the world have a wealth tax, so people are not forced to declare wealth data. I think France is the only one that I know of off the top of my head. There are proxies for wealth taxes in places like the United States. For example, inheritance tax, capital gains tax are sort of proxies for wealth tax.
What does it look like when you plot out the rate at which the Gini curve is changing?
I don't have that on my slide, but roughly speaking, off the top of my head, in 1989, the Gini coefficient of the United States was about 78%. And in 2013, it was about 86%, as you saw.
So you can extrapolate that. Is there like a breaking point or a point where you just don't think that it would just eat the rich people? I mean, at what point is there some other mechanism to kick it back the other way? Because there's going to be some point where it's just not practical.
Yeah, there are many assumptions here, and that's a very good point. We're not including here population growth. We're not including immigration and emigration. Our N is constant. Now, again, in the Lorenz curve, you scale out N anyway. You're only looking at fraction of people, so maybe that's okay, but maybe it isn't. Likewise, we're assuming wealth is conserved. We're not including production and consumption. Those are surely important effects, but to some extent they cancel. For many people, what they produce, they consume. At the top of the wealth spectrum, that's not true. They produce far more than they can consume. None of that is included in here, so including those can presumably only make it more accurate, or we would hope that once you include all those things, then you might also look at this business about the delta W being proportional to the minimum of the two wealths. You might look at wealth attained advantage being a probability bias that's proportional to the wealth difference. There's all kinds of little models built in here that are kind of reasonable, but all of them warrant some examination. Yeah?
I was just wondering, all the countries in the world, which have, I guess, the closest to egalitarian wealth distribution? And is there been studies of that and correlations with happiness of the population there, et cetera?
I don't know of, to answer the latter question first, I don't know of any studies like that. I know there is one country, Bhutan, that has decided that it wants to focus, rather than on economic growth, on some measures of happiness of their population. And they've gone a long way toward trying to quantify that. But To go back to the first question, what are the most egalitarian countries in the world according to wealth Gini now? According to income Gini, you get very different answers. So let me add that caveat at the beginning. Japan and China are close to the, oh, careful here. No, sorry, Japan is close to the bottom of the wealth Gini. I think its wealth Gini comes in at about 60% or so, but I'm forgetting the exact number. Most Western European countries are somewhere in the low 70s or mid 70%. There are a few exceptions like Switzerland and Denmark that are closer to where the United States is. How many, aside from them, and I forget whether those two countries are within a tiny amount of the United States. How many countries are above that? It's Zimbabwe and Namibia, I want to say. Period. Every other country in the world besides those four have lower Gini coefficients than the United States. When you flip to income Ginis, the answer is a little bit different. For income Ginis, Scandinavia are very low remember that income Ginis are generally lower. Scandinavia is in the low to mid 20% range, and those are some of the lowest in the world. US income Gini and the Chinese income Gini are both in the high 40% range. Most of Western Europe is in the low 30% range, but it varies dramatically between Northern Europe and Southern Europe, as you might expect, and so forth.
Just one, perhaps last question.
Uh-huh.
Is there any sense that something like this can be applied also to income inequality? Other than just wealth? I know that it's completely different, kind of like when...
Yeah, it's possible, but it would have to be a very different model.
Right.
And I think even the tails of the distributions are quantitatively different. The tail of the wealth distributions that come out of our model are, when you go through the mathematical analysis, provably in their mid-range, they descend like power laws, and way up at the top, they actually have a Gaussian cutoff. I don't think that's true of income distributions. I think it's closer to a power law all the way down. That's the famous Pareto distribution, is a power law all the way to the tail for income. So there are some real differences between them, and it's sort of important not to mix them up.
Would it be convincing to try to predict before the 2016 data gets heard? Predicted? I mean,
The 2016 data is out now. It's been out for about 3 weeks or so. I have I have a student that works on some of these fits, and I don't know that she's done that yet. But I don't know that we could predict it. The U.S. is a stable enough economy, and this is true of most of Western Europe as well, that you can sort of neglect. It's a dynamical equation for the distribution. But we got all these answers by just neglecting the time derivative term and looking for the steady state solution. The optimist way of saying that is that it didn't matter so much, and we were able to get good results by just assuming that the economy was in a quasi-steady state. The pessimist way of saying that is you haven't tested the time-dependent term in your dynamical equation for the wealth distribution, because you haven't found an economy unstable enough to test it yet. That's why we're looking at the former Soviet Union. If we can get data from there between 1988 and 1998, you surely cannot neglect the time derivative term in that case. And as best as we can see, the Gini coefficient of Russia, for example, increased dramatically between 1990 and 1995. There's no way that you could neglect the time-dependent term there. But we don't quite trust the data that we've got enough yet to do that analysis. I'm optimistic that we'll be able to do it.
Let's thank our speaker.
Thank you.